Once humankind was more like a wild beast, spending most of its time in finding food. Then somehow, men learned to cultivate land and grow crops. This happened 12,000 years ago, and historians call it the First Revolution or the Agricultural Revolution. This great learning has transformed our lives by providing and preserving plenty of food, so we can do a lot more than just hunt. With the passage of time, our methods have also evolved. From manually planting crops to raising poultry, we now rely on cutting-edge technologies. Today, you see pest drones, advanced irrigation systems, autonomous robots, and much more. These technologies are going hand in hand with farmers to maximize yield and produce enough food to feed everyone. To give you a glimpse of the progress made in agriculture, let's rewind to a few decades back. Originally, agriculture was solely based on manual labor and natural methods. This is what most know now as Agriculture 1.0, and it involves planting seeds, tending to fields, and harvesting crops using simple tools like hoes and scythes. Agriculture was a tedious job during this period. Farmers still did not know much about the science behind farming. It was the first industrial revolution when farmers made considerable progress by including the use of machines for farming. The steam tractor is one of the outstanding examples of this time. This era is known as Agriculture 2.0, in which the transition from manual labor to mechanization has significantly improved efficiency on larger-scale commercial farms. Farmers and specialists also started looking for ways to boost crop output. Thus, much research was focused on generating high-yield types of crops. Given the things happening, experts in the field thought of adding the use of advanced technologies and digital innovations to agriculture. This is now known as Agriculture 3.0, and it has initiated the popularization of sensors, drones, satellite imaging, and more. The central goal of the techniques formed during this time is to produce more food with fewer resources, reducing the environmental impact while ensuring better profitability for farmers. This time, farmers have moved towards the goal of minimizing environmental impacts such as soil degradation, water pollution, and energy consumption in agricultural processes. In one way or another, this goal was achieved by transforming traditional methods of cultivating crops into more efficient ones. Instead of relying on manual intervention, the processes in this era have been automated and powered by machine learning algorithms driven by big data analysis systems. In this way, farms are able to produce high-quality products without using a lot of resources. One of the biggest issues the field of agriculture has been facing is global warming. The crops and other agricultural products heavily rely on the weather, but global warming makes it very unpredictable. One moment the farmers are getting ready for a flood, then the next they are stressed out about droughts. Ample water supplies are necessary for agricultural activity, but during droughts, these resources become scarce. Reduced crop yields can result from drought circumstances because there is insufficient water for plant growth. These incidents of drought have damaged not only the crops, but also human lives. Since 1900, more than 11 million people, about twice the population of Arizona, have died, and more than 2 billion people have been affected by drought. But we have already come a long way in agriculture. Now, these issues have solutions and preventions too. Agricultural 4.0 has brought about a major change in farming practices, doing away with conventional approaches that mostly depend on the consistent application of herbicides, fertilizers, and water. Doing away with conventional approaches that mostly depend on the consistent application of herbicides, fertilizers, and water. Rather than using excessive amounts of resources, farmers will start using precision agriculture methods to increase crop yields. This groundbreaking strategy will prioritize environmental sustainability and safety in addition to increasing revenue. The integration of cutting-edge technologies such as sensors, gadgets, machinery, and information technology is the cornerstone of Agriculture 4.0. Thanks to these advancements, farmers can now monitor their crops with a level of accuracy never before possible, enabling them to spot and fix certain problems that are impacting their farms. Farmers can modify irrigation schedules based on changes in soil conditions, for example, which can be detected by temperature and moisture sensors. Real-time data on crop health, growth patterns, and soil nutrient levels are made possible by aerial photography and GPS technology. Now, it's the age of agriculture 5.0. This next step goes beyond mere optimization and efficiency. One of the most important developments for agriculture is the Global Positioning System, GPS. Although this is not a new technology, this has helped strengthen the use of machines and intelligent systems in agriculture. By giving farmers access to exact position data, GPS technology has revolutionized agriculture by empowering them to manage their crops, tools, and resources more effectively. Field mapping is one of the most important uses because it helps farmers plan their crops and conserve resources by identifying specific soil types, water levels, and slope inclinations. Crop monitoring checks, crop health, growth stages, and yield estimates, enabling farmers to make timely decisions on irrigation, pest control, and harvesting. Guided farm equipment utilizing GPS lowers fuel use and targets input utilization. GPS-enabled livestock tracking also helps with early disease detection, grazing pattern management, and reducing losses from stray animals or predators. GPS is also helpful when it comes to operating tractors. Different farming equipment can navigate fields with accuracy thanks to GPS-based guidance devices. Time and materials are saved significantly because of this system's reduction of overlap in planting, fertilizing, and harvesting. Not to mention that this also helps minimize operator fatigue and increase field efficiency. In most machines, the auto-steering technology makes sure that the equipment stays on course. Another technology that has helped develop agriculture is the mapping and tracking technology. To be more specific, John Deere offers the AutoTrack turn automation. In order to maintain regular crop growth and health, this system automatically regulates the entire headland turn, raising or lowering connections at the appropriate time and location in the field. It lowers input costs for gasoline turn automation and seed fertilizer by integrating John Deere AutoTrack automatic steering and headland management into 6 R29 tractors. Operators may preview impending turns and modify turn direction or skips with ease because of the new, intuitive generation of displays, which also makes interface configuration easier than before. With this technology, even experienced operators can benefit and always achieve a flawless headland turn. Furthermore, they also created the AutoPath. This program uses crop row maps created during the initial run across the field, whether it's a planter base or strip till, to automatically create guiding lines for farmers. To map the data, farmers merely need to install an implement receiver on their strip, till or planter. Nothing changes after this, and planting, spraying or harvesting is made simpler on the second pass. Regardless of the breadth of the equipment, AutoPath generates guidelines automatically throughout the entire field. Mapping and tracking technologies provide valuable insights into fields, helping farmers overcome challenges and improve crop yields. Using these technologies, a lot of issues can be resolved or prevented. For example, farmers no longer have to be worried about overlapping during planting because these systems record where the crops are placed. Improved row spacing is another advantage of mapping and tracking systems. Maintaining equal growth and optimizing yield depend heavily on maintaining consistent row spacing. Crops may fight for resources if they are not spaced properly, which could result in stunted growth and lower yields. Farmers may guarantee that their rows are regularly spaced, leading to healthier crops and larger yields. Thanks to these technologies, the creation of autonomous tractors was made possible. The potential for autonomous tractors to transform agriculture has drawn a lot of attention in recent years. To complete jobs without human assistance, these machines make use of cutting-edge technologies, including machine learning algorithms, automatic steering, and GPS guidance. John Deere, Case IH, and Trimble are among the businesses spearheading the development of autonomous tractors. While some models are still in the testing stage, others are now available for purchase. The enhanced efficiency of autonomous tractors is one of their primary advantages. Through route optimization and the elimination of manual labor, These machines are able to cover a greater area faster. They can also lower pollution and fuel usage, which is good for the environment and farmers alike. There are essentially two types of autonomous tractors, the semi-autonomous one and the fully autonomous tractors. John Deere has developed a semi-autonomous tractor where the operator no longer has to ride the tractor to operate it. Thanks to its built-in cameras, GPS, and other smart systems, the operator can make the tractor work remotely. This tractor also has an integrated crop sprayer, and it is programmed to spray tree by tree. It can easily navigate its way through the rows of crops because of its vision row guidance. Now, the operator no longer has to be exposed with the chemicals it sprays. John Deere has recently unveiled their latest innovation, the autonomous 8R tractor. This cutting-edge tractor is equipped with state-of-the-art components and applications like Starfire, receiver, auto-track, turn automation, and John Deere Operations Center, which work together seamlessly to enable the tractor to operate independently. At the heart of any autonomous tractor's operation is its high-speed processor, which evaluates every pixel of every image captured by the tractor's 360-degree cameras. These cameras provide complete visibility of the field, allowing the tractor to triangulate distance and accurately navigate through even the tightest spaces. Additionally, a neural network processes all visual data to ensure accurate object detection and decision-making. With the ability to automatically steer, accelerate, and brake, the autonomous 8R tractor can perform a variety of tasks without any human intervention. But how are both types of autonomous tractors different from each other? Compared to fully autonomous tractors, semi-autonomous tractors have less automation features. Even while they frequently have cutting-edge features like GPS guidance, automated driving, and cruise control, many operations, including planting, spraying, and harvesting, still need to be done by humans. Conversely, fully autonomous tractors require little to no human assistance to carry out any task, from planting to harvesting, on their own. Tractors that are semi-autonomous mostly depend on human operators to make judgments and fix any problems or mistakes that occur while they are operating. Fully autonomous tractors, on the other hand, make decisions and maneuver the field without the need for human aid by utilizing sophisticated algorithms and sensors. Because of their sophisticated sensor technology and artificial intelligence, AI, fully autonomous tractors are better able to adjust to shifting environmental circumstances and unforeseen impediments. Tractors that are only partially autonomous can find it difficult to adapt to unanticipated events without human assistance. But autonomous tractors are not the only technological advancements in agriculture. In agriculture, small robots are becoming more and more common for a variety of purposes, including assisting with harvesting, identifying pests and illnesses, and monitoring crop health. These compact devices are able to move easily through fields and crops, giving useful information and increasing crop yields. The use of small robots in agriculture is growing as a way to lower expenses and enhance crop quality. While airborne drones employ high-resolution cameras to detect problems like water stress and disease outbreaks, autonomous ground robots utilize sensors and cameras to collect data on soil, moisture, temperature, and crop development. Robots that operate underground keep an eye on the state of the soil and plant seeds at specific depths. Self-driving tractors ensure uniform seeding and fertilization procedures while saving time, fuel, and labor by navigating fields using GPS and machine learning algorithms. Harvesting robots help in fruit and vegetable picking by identifying ripe produce and carefully removing it without harming crops or the environment. They do this by using mechanical grasping devices and computer vision. These robots are essential for lowering waste and the impact on the environment in agriculture. Let us get into their specific uses. They can be used to help with weeding, for example. These autonomous robots navigate across fields, utilizing AI and sensors to identify weeds. They physically eliminate weeds using revolving drums or spinning blades, leaving the area clear and prepared for planting or fertilizer. They distinguish weeds according to their size, shape, color, and growth patterns using machine learning algorithms. After identification, the robot preserves the intended crop by chopping the weed at the soil surface. This focused strategy increases crop yields while minimizing the use of herbicides and lessening their impact on the environment. Numerous applications of robotics technology have revolutionized harvesting, a critical component of agricultural productivity. For instance, a large number of farmers have begun utilizing driverless harvesting vehicles. These autonomous combines and pickup trucks are outfitted with sensors, GPS, and artificial intelligence, AI, algorithms to enable them to traverse fields on their own, precisely identifying and gathering ripe crops. These devices assist farmers in increasing yields and lowering expenses related to unsuccessful harvests by maximizing harvesting periods and minimizing labor shortages. Additionally, they offer precise fruit-picking robots made for vineyards and orchards. These robots recognize ripe fruit and carefully pluck it from plants without harming crops or the environment. They do this by using computer vision and mechanical grasping devices. By minimizing waste and improving quality control, farmers can focus more on sustainability, food safety, and producing healthier crops. Understanding the health of an orchard is crucial for farmers, as it directly impacts yield and quality of produce. Mammut, an autonomous robotic platform powered by artificial intelligence, is an innovative solution. It integrates sensors like stereo cameras, LiDAR, IMU, compass, wheel odometers, and an onboard AI system to map and navigate its surroundings without relying on GPS or fixed radio infrastructure. Mammut's sophisticated blend of technologies allows it to know its location and navigate through new environments in real time. Stereo cameras provide high-resolution images, while LiDAR creates detailed point clouds for accurate obstacle detection and distance measurement. IMU and compass ensure stable orientation and navigation, even in GPS-denied environments. Wheel odometers track distance traveled, and the onboard AI system performs simultaneous localization and mapping, SLAM. Mammut's practical applications include collecting valuable data below the canopy, enabling farmers to treat each plant individually and on the scale of massive industrial farming. It also allows farmers to focus on other tasks while the platform performs its duties, increasing efficiency and saving time. By giving farmers access to a multitude of useful data and empowering them to carry out chores more effectively than ever before, drones have completely changed the agricultural industry. Drones are revolutionizing this business in a number of ways, including precision farming and crop monitoring. One of the main purposes of drones is in spraying, by applying pesticides, herbicides, and fungicides directly to particular crop areas. Drones fitted with spray nozzles or other applicators can minimize waste and chemical usage. By using a targeted method, non-target plants and animals are protected from overspraying. Farmers can ascertain the ideal quantity of chemicals required for various areas of their fields by examining data gathered by drones. These parameters include soil type, crop growth phases, and moisture levels. With this variable rate spraying technique, disease and pest management are effectively maintained while using fewer chemicals overall. Farmers may configure precise paths and application rates for their unmanned aerial vehicles, UAVs, by using automated spraying systems that are integrated into certain drones. This guarantees uniform coverage across whole fields and removes the possibility of human error in manual spraying procedures. In addition to that, drones are being used to monitor crops. Equipped with cameras, these unmanned aerial vehicles, UAVs, capture high-resolution images of fields and crops, allowing farmers to track crop health, growth, and development. This enables early detection of issues such as pests, diseases, or nutrient deficiencies, giving farmers the opportunity to take action before the situation becomes critical. For example, if a drone captures images showing signs of pest infestation, farmers can apply targeted treatments rather than blanket spraying entire fields, reducing chemical usage and minimizing waste. Drones are being used to predict crop yields, allowing farmers to make informed decisions about harvest planning, resource allocation, and pricing. This helps reduce uncertainty and allows for better resource management. Drones also have sensors that detect soil moisture levels, temperature, and other parameters, providing valuable insights into irrigation management and fertilizer application. Soil analysis is crucial for optimal plant growth and health, and drones make it easier for farmers to gather this information without physically checking each plot of land, saving time and money while ensuring more accurate results. Now, drones are also used for insect control. One example is this bat-like drone, which serves as an artificial predator that intercepts moths mid-air. The drone's purpose is to keep an eye on and manage moth populations in greenhouses in order to prevent plagues and preserve ecological equilibrium. Growers may feel secure knowing that their drones are constantly prepared for action thanks to the autonomous bat system's pest control measures. The drones stay inside and never sleep in order to minimize their negative effects on the environment. For greenhouse growers, this novel method of insect management holds great promise as it offers long-term control while safeguarding crops. Drip irrigation is a method of crop watering that delivers water directly to the roots of plants, drop by drop, through a network of tubes and emitters. This technique allows for precise control over the amount of water each plant receives, which can lead to increased crop yields and reduced water waste. Drip irrigation systems typically consist of a series of polyethylene pipes that run along the rows of crops, with emitters spaced at regular intervals. The emitters release water into the soil around the base of the plants, allowing it to soak in slowly and reach the root zone. One of the main advantages of drip irrigation is its ability to conserve water. By delivering water directly to the roots of the plants, rather than spraying it overhead, drip irrigation reduces evaporation and runoff, resulting in more efficient use of this precious resource. Subsurface drip irrigation, SDI, is a cutting-edge technique for irrigating crops that uses a system of underground pipes and tubes to send water straight to plant roots. Water is supplied more slowly in SDI systems than in traditional flood or sprinkler irrigation techniques, enabling a more accurate distribution of moisture throughout each plant's root zone. The subterranean location of the pipes also helps decrease weed growth and minimizes soil erosion. Controlled water supply can also result in improved nutrient uptake and more effective use of the water resources that are available. Water is delivered directly to plant roots in both drip irrigation, DI, and subsurface drip irrigation, SDI. But there are some distinctions between the two techniques. For SDI, the emitters are usually buried underground, but for DI, the emitters are positioned at regular intervals throughout the length of the tape using above-ground tubing. Another key contrast is the application regions in which they are typically utilized. While bigger commercial farms frequently choose SDI because of its higher efficiency and capacity to cover wider areas, smaller-scale gardening operations and vegetable production typically use DI. In other sugarcane plantations, they make use of subsurface drip irrigation. First, they plan and design the structure of the irrigation. This is totally dependent on the field and the positioning of crops. After that, they install the drip system. It is important to note that distance between each line should be consistent. In this case, it is in the range of 1.5 meters to 2.4 meters. After they install it, the testing process will begin. This is where they test both the flow rate and water pressure from the irrigation system. If all goes well, the field is ready to be planted with sugarcane. Another type of modern irrigation system is a sprinkler irrigation system. These irrigation systems shine in their ability to cover large areas while minimizing water waste, a key factor in regions where water is scarce. Moreover, these are adaptable to various terrains and crop types, making them a versatile tool for farmers. They are popular for their versatility and efficiency, but they require energy to pump and pressurize water, and can be more expensive than surface irrigation methods. The sprinkling irrigation system usually consists of a pump that draws water from a source such as a river, well, or reservoir, ensuring that the plants receive a uniform water supply. This water is then channeled through pipes to a central tower or pivot point. From there, it's distributed to an array of sprinklers. The heart of these systems is the center pivot, which is moved by electric drives with minimal horsepower. These drives are finely tuned to accommodate the unique dimensions and terrain of each field. Such precision in water distribution takes into account the varying soil types and topographical features, leading to enhanced water application accuracy. This tailored approach not only conserves water, but also significantly boosts production by providing optimal irrigation specific to each area of the field. As what we mentioned earlier, one of the most pressing issues agriculture has been facing is its problems with climate change. Good thing that the technologies developed now are more centered on how to solve them. One of the ways they thought to counter the ever-changing climates is through greenhouses. Transparent or translucent materials are used to build greenhouses, which let light in and warm the interior, improving the growing conditions for plants. They are frequently employed in horticulture and agriculture to increase crop yields, lengthen the growing season, and shield plants from inclement weather. Greenhouses come in a variety of sizes and designs and can be either freestanding or fixed to a building. The most popular kind of greenhouse is the glass greenhouse, which regulates temperature and lets in natural light through sheets of glass. Other varieties are hydroponic greenhouses, which use nutrient-rich water instead of soil to support plant development, and plastic greenhouses, which cover the frame with films of polyethylene or polypropylene. But it does not stop there. We also have vertical farming. Growing plants in vertically stacked layers or columns, often with hydroponic or aeroponic systems, is known as vertical farming. This technique minimizes the need for land and water while maximizing the use of available space. It can be employed in urban locations where traditional agriculture might not be possible, and allows for year-round output. Vertical farming is frequently used to raise leafy greens, herbs, tomatoes, cucumbers, and bell peppers, among other crops. Both hydroponics and aeroponics are soilless gardening techniques that supply vital nutrients straight to the roots of plants. The way the plants get these nutrients is where the main variations reside. In aeroponics, nutrients are misted on a regular basis as the roots hang down into the air, while in hydroponics, plants are maintained in a nutrient-rich solution as opposed to soil. Aeroponics may be an excellent option for smaller installations or those trying to reduce water use, although hydroponics is typically better suited for larger businesses. In the context of vertical farming, a vertical tower is essentially a tall column that is used as a plant-growing medium. A comparatively small footprint may support several stages of crop cultivation thanks to the tower's ability to be stacked together to maximize space. The substrate material in the towers, which gives the plant roots support and nourishment, is typically rock wool or coconut husk. These towers are capable of producing large amounts of fresh food year-round with the right lighting and irrigation systems. The hydroponic fodder farm involves a lot of processes. First, it starts with soaking 130 pounds of barley seed overnight in a hopper and draining it into a push cart. This process removes contaminants and breaks the seeds' dormancy, allowing them to sprout. The seeds are spread evenly in trays, and after 2 days, sprouts appear. Specialized hardware and software are used to control the farm's environment through a digital screen. The feed can be harvested after growing for 6 to 7 days. Because the roots spontaneously join together to form a mat, the soilless growing method is unique and facilitates easy harvesting. The whole mat of fodder roots is edible, very nutrient-dense, high in protein, and helps keep animals more hydrated. It takes 2 to 3 hours a day to maintain a clean hydroponic fodder farm, which lowers the risk of pollutants like mildew. On the other hand, this part shows the process of Green Automation's automated growing system. This system is designed to assist in head lettuce production. The system is designed for growing head lettuce and herbs, and uses principles of vertical farming from the seeding down to harvesting. The lack of connectivity is one of the main issues when implementing IoT equipment in rural areas. Farmers must be aware of the entire layout of their farm, including what's above and below the ground, in order to implement precision agriculture. All of these distinct data streams can be combined with the aid of artificial intelligence and computer vision techniques to provide perspectives of the farm that would not be possible to access otherwise. 15 to 20 gigabit of data can be created and instantly returned from a single drone trip. Using self-reinforcing loops, field management can become more granular, going from field-by-field management to acre-by-acre management, or even smaller steps. This saves time, costs, and helps control issues on the farm to a better degree. Drones have greatly changed agriculture by giving farmers insightful information on their crops and facilitating more informed decision-making. Drone imaging is the process of taking high-resolution pictures of fields and crops using cameras installed on the drones. This allows data to be extracted, including crop health, growth trends, and yield projections. Better action is made possible by this early issue detection. Drones using multispectral or hyperspectral sensors are able to collect data at particular wavelengths, which improves the accuracy of disease, pest, and nutrient deficit diagnosis. Certain drones additionally employ algorithms based on artificial intelligence to evaluate gathered information and offer suggestions. Drones are therefore turning into a necessary tool for contemporary agriculture. Agriculture has undergone a revolution thanks to wireless sensors, which make it possible to monitor temperature, humidity, and other critical elements for crop health in real time. These sensors send data wirelessly to a central system for analysis. They can be powered by batteries or solar panels. Instead of depending only on weather forecasts or visual inspections, this enables farmers to make well-informed decisions about irrigation schedules, fertilizer application, and pest management based on actual conditions in their fields. Wireless sensor networks can also offer early warning systems for possible dangers, like disease outbreaks or severe weather. Precision agriculture is a technology-driven agricultural method that gathers data from fields and livestock remotely using sensors and equipment. A major obstacle is the restricted internet availability in rural areas. In response, creative professionals in the field have created specialized antennas that function inside television frequency ranges, enabling higher penetration through obstructions such as buildings or trees. By enabling dependable connectivity even in the absence of cellular networks, this facilitates the use of Internet of Things (IoT) sensors linked to collars or tags to track the position of animals and monitor crop health and soil moisture levels. Because they give farmers access to real-time information on temperature, humidity, wind speed, precipitation, solar radiation, and other environmental elements that might affect crop development and yield, weather stations are essential to precision agriculture. With the use of this information, farmers are better able to control pests, apply fertilizer, harvest crops, and regulate irrigation, all of which increase yields and improve profitability. In order to produce more precise forecasts of crop health and yield, weather stations can also be combined with precision agricultural technologies like drones, satellite imaging, and machine learning algorithms. Artificial intelligence, AI, has transformed several industries, but the agricultural sector may be the one most affected. AI applications are already beginning to improve agricultural quality, reduce waste, and optimize resources through tasks like evaluating satellite photos and forecasting crop yields. The advantages are numerous and include improved production and efficiency, as well as sounder judgment and environmental sustainability. Artificial intelligence, AI, is revolutionizing agriculture, arguably more than any other industry. Through AI, the quality of agriculture is enhancing, waste is reducing, and resource optimization is becoming more effective. This transformation is driven by AI's capability to process and analyze vast datasets from sources such as satellite imagery, weather forecasts, and soil sensors. This analysis results in more accurate and efficient farming techniques. The benefits of AI in agriculture are manifold, including heightened production efficiency, better decision-making, and enhanced environmental sustainability. AI is not just incrementally improving agricultural practices, it's redefining them, paving the way for a more prosperous and sustainable agricultural future. Hope you guys have enjoyed the technological saga of Agriculture 5.0. Let us know what would happen next in Agriculture 6.0 in the comments below, and feel free to check our other videos. Thanks for watching.